Thank you very much. As I'm Jay Parlar, at Parlar on Twitter. I'm a software developer at Rackspace. Thank Rackspace for sending me out here today, but mostly I want to thank my friends at Rackspace for listening to me talk about TLA Plus nonstop all year, putting up with me. I do appreciate that. So TLA Plus is a system design language. It says PlusCal up there as well. TLA Plus and PlusCal are technically different things. For the purposes of today's talk, though, the difference doesn't matter, so I might use the terms interchangeably. And by the end of this talk, I hope you'll understand what I mean by debugging software designs with testable pseudocode. Now, I want to say TLA Plus is not a programming language. It looks like one. PlusCal especially looks like a programming language, but you do not use it to write code that runs on a server somewhere. You don't live in the blueprints of a house. Instead, blueprints are put together to help design the house and then guide the construction of the eventual house that you can live in. TLA Plus is very similar. You don't use it to write your final software, but you do use it to design your software, automatically detect really terrible bugs early, and then use your TLA Plus specifications to guide the implementation of the eventual Python code that you're going to write. And I'll say TLA Plus can be used for any kind of software, literally any kind, from designing a small, simple algorithm to a globally distributed, multi-server, concurrent, fault-tolerant communication system. Like anything along the way, you can use TLA Plus for it. Now, using TLA Plus to help design your software has a lot of benefits. One of the big ones being is that it's been shown that if you can identify a bug in the design phase, as opposed to only finding that bug once it hits production, it is literally orders of magnitudes cheaper and easier for your company to fix. Now, I know what you're all thinking. You're looking at this and saying, that looks a lot like waterfall. And we're all agile. Everyone's agile these days. We don't need to do design because we're going to do a lot of sprints. We're going to do a lot of iterative development. We're going to deploy every hour. We're going to have tons and tons of test-driven development. And that's all fantastic. And a lot of software can and is built just like that. But it has been proven time and time again that actually thinking about what you're going to build before you go and build it will give you higher quality software. All right, so I'm not saying get rid of Agile. This is kind of an older slide here, but I want to point that out. All right, and the place where design can be most important with TLA Plus is when you're talking about concurrency or distributed systems. Now, probably every single person in here is working on software that is a distributed system. It's very rare to have software anymore that doesn't talk to APIs or doesn't receive network requests. Everything these days is basically a distributed system, and TLA Plus can really help with that. So to give an example of the use of TLA Plus, I'm going to show you the simplest possible banking system you can ever imagine. This example itself comes from a website called learntla.com, which is an amazing, amazing resource, and it really helped me learn TLA. So in this banking system, there's only two customers, Alice and Bob. When the banking system starts up, they're both given $10 initially. The banking system is only allowed to do one kind of operation, and that is a transfer from Alice to Bob. And it can only do one of that operation, and then the system is complete. That's it, nothing else to it. The only requirement that we have is that Alice's account must never go below $0. All right, she can't be overdrawn when she does this transfer. So what I want to do is I want to talk through how simple this design is in the simplest way. Then I want to add a little bit of concurrency, just the smallest amount of concurrency. I want to show you how unit tests would never be able to test for a little tiny bit of concurrency, or successfully 100% of the time not test for it. And I want to show you how TLA Plus can help identify a race condition nice and early. So how would we design this super simple system? All right, and we're just talking about the design. We're not talking about the network sockets that are going to come up and listen for the incoming transfer request. I just want the core logic of the system designed. And this is the design. This is some pseudocode here. There's nothing to it. This is the entirety of that banking system that I described. A transfer comes in. If Alice has enough money in her account, then we take it out of her account, we put it into Bob's account, and the system is done. The bank shuts down for the day. That's it. That's the entirety of the system. And this design is correct. For the requirements I gave, there's no bugs here. Everything's great. What happens if we add just the smallest bit of concurrency to it? Instead of allowing one transfer, I want to allow two transfers. And I want each of those transfers to be handled in a different thread, or a different process, or maybe even two different servers on opposite sides of the world. It doesn't really matter. I've labeled the threads transfer 1 and transfer 2. The code in them is the same, except that thread 1 uses that pink transfer amount 1 at the top, and thread 2 uses the green transfer amount 2. So they're each transferring potentially different amounts of money. Same requirement holds. Alice has to have at least $0 in her account at the end of the day. So again, these are the only things that are really separate about what we've got here. Now, because there's concurrency, we're going to need some kind of locking or transaction or something, right? We've got multiple operations happening here. So I don't want to worry about, in my pseudocode here, I don't want to worry about instantiating locks and explicitly locking and releasing them, or database transactions, because maybe you would do the atomic stuff as a database transaction. It really doesn't matter. I just want to easily in my pseudocode identify the atomic sections. So the first one, I've labeled it condition 1, and there's a blue box around it, and that means that that line of code is guaranteed to happen atomically. Alice account will not be modified while that block of code is being run there, while that one line is being run. Same thing for thread 2. I've labeled that as condition 2. For the actual transfer, I want the money to come out of Alice's account and go into Bob's account as a single operation. So I've put a box around all of that, labeled it do transfer 1. That might be a database transaction. It might be explicitly locking objects to make sure nothing else can modify them. Doesn't really matter. And the same thing for thread 2, do transfer 2. So now we have two threads. They do almost nothing, and each of them has two atomic sections in it. So let's squish these up to the top of the screen. I've put some boxes around them to help you keep in mind that these are separate threads. It's not one continuous block of code. So given this very tiny concurrent system, what are the possible interleavings of these atomic actions? Like, they're going to happen in some order. Do we know what that order is? Well, at the end of the day, we don't. It might be that the transfer requests come in at the network at vastly different times. It might be that they come in at exactly the same time, but who knows which order the operating system is going to be servicing the network stack, which socket it's going to pull the transfer from first, right? Or we're talking about threads or processes. Who knows how your operating system scheduler works? Which thread is going to be executing at any given point in time? The only thing we know here is that condition 1 is guaranteed to happen before do transfer 1, right? And we know that condition 2 is guaranteed to happen before do transfer 2. But do we know whether condition 1 or condition 2 will actually execute first in a real live system? We don't. It's non-deterministic. And computers, unfortunately, are filled with non-determinism. Now, this is a small enough example that I can actually manually figure out all the possible interleavings. So what's one of them? Well, it might be that condition 1 happens, and then do transfer 1 happens. Then condition 2 happens, and then do transfer 2 happens. And that's fairly straightforward. It might also be that condition 1 happens, and then the operating system pauses that thread, spins up thread number 2, runs condition 2, pauses thread number 2, goes back to thread number 1, does do transfer 1, pauses thread number 1, goes back to thread number 2, and does do transfer 2. This is a possible interleaving of these atomic sections here. And in total, for this particular example, there are 6. Now, because this example is so small, it's actually possible for me to explicitly enumerate all the ways that the threads can interleave with each other. But in a real system, there's no way you can do that. Right? There's almost infinite combinations of interleavings of atomic sections. So given this tiny system, if you were to go and implement just what we have here in Python, how would you write unit tests for this? How would you write unit tests that guarantee you've covered all of these interleavings of threads? That's really hard. Programming languages aren't made to do that. You could add some extra locks into your system that are really only there to be serviced by tests and try to explicitly do what your operating system's thread scheduling algorithm does. But the odds of you getting that right, even for a tiny example like this, are basically impossible. And when you talk about a real system with maybe different services running around the world on different clouds, all talking and sending messages at the same time, there's no way you can test for that. And that's where race conditions come from, because we can't test for this. You could try to write tests for this that pass 1,000 times in a row, then you put the code into production, and within 1 minute, Alice's account goes below $0 because you have a race condition here. There is a bug in this. but your tests never found it because they never happened to be run with the operating system scheduling them in a very particular way. So what I want to show you now, after 10 minutes, is what TLA Plus looks like to try to do this simple example. So I'm not brave enough to do a live code demo, so what I've done is taken screenshots of a live code demo. And what you see here is the TLA Plus toolbox. On the left is the editor, on the right is the model checker. For some reason, only the left side lets you increase the font. I apologize for that. You'll have to trust me that there's interesting stuff on the right side there. So on the left, we have the TLA Plus specification for this design. All right, it's very simple. It should mostly be readable based on everything that we've talked about so far. All right, a couple things to point out. On line 12 and line 22, we use the TLA Plus process. It's the same as the thread. It's the same as a process. It's just telling TLA Plus these two chunks of code are going to operate independently. They're just going to run and do their thing. A couple other things to point out is these labels here. So the way I specified atomic sections before in the pseudocode, that's how you do it in TLA Plus as well. So line 13 says, start a new atomic section here. Everything that happens after it is going to be done as one atomic operation until we hit the next label. And that's when this atomic operation stops. So that means that line 14 happens as a single atomic operation, and that line 16 and 17 happen as a single atomic operation. Thread 2 at the bottom there has exactly the same thing. Now at the top, we have the variable declarations. Alice account equals 10, Bob account equals 10. That should be straightforward enough. But what's interesting is the transfer amount 1 and transfer amount 2 declarations here. We haven't really spoken about those values yet and what they might be. So what I'm telling TLA Plus here is that transfer amount 1 could be any value from 1 to 20. And transfer amount 2 could be any value from 1 to 20. So how many combinations of initial values does that give us? It gives us 400. 20 times 20. There's 400 different ways to have combinations of those values there. So right away, without having to think about injecting 400 different values into a unit test, you have to do something very explicit for that. With TLA Plus, it's not the case. I'm just telling TLA Plus, hey, this variable could take any value in this range, and this variable could take any value in this range. Go figure out every single possible combination. And then keep in mind the last slide where we were looking at the interleavings. We know that for this system, there's 6 different ways that the atomic sections might interleave with each other. And TLA Plus can figure that out on its own as well. So we have 400 possible initial values for the variables and 6 interleavings. It's going to try every one of those 400 combinations with all 6 interleavings, meaning right away we've generated 2,400 tests. All right, it has exhaustively tested this pseudocode. It's figured out every single way this pseudocode can run. Now, what we haven't done yet is asserted anything. If you're writing a Python unit test, you have to have an assertion and assert something is true. If it is not true, you have a bug. So how do you do that in TLA Plus? Well, in very tiny text on the bottom right there, I'll blow that up for you because I accounted for this eventuality. You can list invariance. If you're not familiar with the term invariance, it means a property that must always be true. So we're saying here that we want the Alice account variable to always be greater than or equal to 0. And if TLA Plus ever finds a way to execute that system such that the variable goes below 0, it's going to stop, raise an error, and say, hey, you've got a bug in your design. So let's go back. To actually run this, I would click on that little tiny green button up there, which I couldn't make any bigger. I'm not going to blow that up. It's a green button. If you do click on it, after 2 or 3 seconds, you're going to get a third panel on the right, which I know you also can't read. I accounted for that as well. I know you probably can't read the top. I accounted for that too. What it said is it tried to run this system, and it found a case in which our invariant was violated. It found a way for that variable to go below $0. And what it's showing at the bottom here is roughly equivalent to a Python stack trace, except it is approximately 1 million times better. Why is it 1 million times better? Well, a TLA Plus stack trace shows you the value of every single variable in the system at all points through leading up to the error. When you have a Python stack trace, you've got the function calls that chained up leading it to the error, and maybe you've explicitly added the local variables at the end, and maybe you're doing some sentry stuff to grab more context. But in general, you don't know the state of your system that actually brought it to an error. And if you're talking about a real system, if you have a bug in some service, you don't know what the values of your other services around the world are that were communicating with it at the time that you had the bug. But TLA Plus gives you the entire global scope of all the variables. Now, I'm not going to try to explain how to read that. Instead, I'm going to do some diagrams. So what that was showing at the bottom here is that in the initial state, we had Alice's account at 10, Bob's account at 10, and it happened to be the combination where transfer amount 1 was at $1, transfer amount 2 was at $10. All right, that's one of those 400 combinations of initial variables, or initial values that we talked about. And then for the error it found, it happened to be running the interleaving where condition 2 came first. As a reminder, condition 2 is that line of code. Now that line of code doesn't modify any variables, right? It just does read. So that means after that atomic section is done, our system is in exactly the same state. Nothing has changed. The next thing the error trace showed was that condition 1 happened next. All right, so thread 2 got spun down, thread 1 came back up, and it executed that line of code. Again, that doesn't change any variables. The condition passes. The state of the system is exactly the same after. And then it did do transfer 1, which was this. So it's going to subtract transfer amount 1, which is $1 from Alice, and add it to Bob as a single atomic action. After that action is complete, what does our system look like? Well, now Alice has $9 and Bob has 11. That's what you want to happen when you transfer $1 from one person to the other. But then we do transfer 2, which transfers $10 out of Alice's account. But we've already done the condition check before, so we've hit a race condition here. Alice now has minus $1 in her account. This is a bug. This is a race condition. It is a problem with the design of our system, with how we set up the atomic actions. And again, you could have written unit tests for this, and the unit tests would never, ever show this error because of how the unit tests happened to run when the operating system was scheduling the threads. All right, so this is the real power of TLA Plus. It can explore the entire state space of your system and figure out if it can ever enter a spot where you're going to run into problems. So just to sort of summarize, what did we just do here? Well, we specified the possible actions, and that means we gave it the possible values for the variables, we gave it the threads, we gave it the atomic actions. TLA Plus can figure out the rest. We specified just a single invariant here. You can specify as many invariants as you want. We just had the one, that Alice must always have greater than or equal to 0. Then I clicked that tiny little green button that you weren't able to see. TLA did its thing, and it found a bug. It found a legitimate bug in this system. All right, so again, for real code, especially something more complex than what I showed you here, if you were trying to find a bug like that just with unit tests, there's a very good chance that your unit tests would never show the bug. All right, and unit tests can't account for all the things that happen outside of your system, all the things that are communicating with it. You do a whole bunch of mocks, you do a whole bunch of other stuff, but it doesn't help with the fundamental correctness of the design of your system. So let's step back away from TLA Plus for a second. I want to go back to the idea of software design. So if you were tasked with writing an algorithm for something, and you wanted to actually do a little bit of design, what might you do? Well, you might write some pseudocode like this. Right? This is actually pretty good pseudocode as far as pseudocode goes. And why would you do this? Well, it helps you get your ideas out of your head and onto paper before trying to appease your compiler or interpreter. Right? You got to think about it a little bit. And it gives you something that you can show to your teammates and say, hey, before I actually start work on this, does this seem reasonable? Does this seem right? You know, it gives you something to think about. And thinking, surprisingly, is a really good thing to do. A couple of my favorite quotes about this is, writing is nature's way of letting you know how sloppy your thinking is. All right? And this doesn't just... It's not just writing, it's also telling someone else. Everyone in here probably has an example of where they thought they understood something, then they went to explain it to somebody and realized, oh wait, I don't actually understand this at all. Or I found a bug in my design. Or just even a PR review. You're walking someone through the code that you wrote and you realize you found a bug because you're forced to explain it to someone else. And Leslie Lamport, the creator of TLA Plus, he said, writing a specification helps you think clearly. Thinking clearly is hard. We can use all the help we can get. Making specification part of the design process can improve design. But let's face it, if you are writing pseudocode, or if anyone's writing pseudocode, it's probably more like this. Incredibly hand-wavy, just pure English, so informal as to be useless, if not absolutely dangerous. Right? This is what most pseudocode is. I don't recommend that. So if you're designing a small little algorithm and the best tool you have is crappy pseudocode like this, how do you design any kind of distributed system, a massively distributed system, a system that has 5 or 6 services talking to each other over a network? What tools does the regular software developer have in their toolbox to help with this? Well, they've got squares and circles, triangles, and tiny little text labels. We have Visio diagrams. This is like the state of the art for software design in most of our industry. Right? And diagrams are incredibly useful. They let you understand how all the pieces of the system fit together, right? But you can't test this for correctness, right? How would you test this for a race condition? You can't automatically test it. You can't really show error cases unless you start doing a whole bunch more diagrams, and that gets really funky because then once the original diagram changes, how do you change all the other ones? Like, it's a visual form of hand waving. It's useful, but it is not enough in itself. Now, engineers in other fields, they produce reams of documentation before they start to actually build something, and they're lucky enough to have math and physics to help prove the correctness of what they're doing, right? But in our field, we have pseudocode and Visio diagrams, and that's not great. So, to quote a Python luminary, Raymond Hettinger, does anybody want to tell me the quote? I know that some of you in this room know what Raymond would say. There must be a better way, exactly. And there is. There's a couple. Most of them actually aren't very good or usable, but there's one, at least, that I think works, and that's TLA Plus. Now, TLA Plus was invented by this fine gentleman here, Dr. Leslie Lampour. If you've not heard of him, he's a Turing Award winner. That's the equivalent of the Nobel Prize for computer science. He invented the Byzantine generals problem. He's the winner of the first ever Dijkstra Prize in Distributed Computing Award. He created the Paxos algorithm, which powers Google Bigtable, Google File System, i.e. the correctness of a lot of the data that flows around Google is in part due to him. And he doesn't even work there. He works for Microsoft. He created the bakery algorithm, which is fundamental to our understanding of how concurrent systems work. He created LaTeX just to make it easier to write papers about this stuff. And he created PlusCal and TLA Plus. So he's brilliant. There's no doubt about that. And I'm Canadian and thus trustworthy. So TLA Plus is probably a good thing, but you would be very right to ask, is this actually usable in industry? Jay, you showed us the simplest example anyone could possibly think of. Lots of academic tools are beautiful at simple examples like that. Does anybody use this on any kind of real system in the real world? Honestly, not a lot of people do, and that straight up, but there are a few companies. There's a couple sort of smaller West Coast startups that have had a lot of success with TLA Plus. So they're called Amazon and Microsoft. If you haven't heard of them, they might not be as small as I'm remembering, but Amazon and Microsoft, Amazon especially, uses TLA Plus extensively. So AWS has major pieces of it that were designed in TLA Plus before they started, hammering away on the keyboard and writing some tests. So what kinds of things do they use it for? Well, at Amazon, S3 has major pieces that are modeled out in TLA Plus before they start writing code. And they found multiple bugs in the design and optimization phases by using TLA Plus's automatic checking capabilities. DynamoDB, fully designed with TLA Plus. They found a bug that would have required 35 exacting steps of exact variables to be in the right order to reproduce in production. Now, that would seem pretty rare, except when you think about Amazon's scale. A bug like that is going to run and hit all the time, except how is a human going to debug a problem that requires 35 exacting steps when you don't have the full state? You have logs from servers all over the world to try to pull it together. You can't do that. EC2, used extensively. They use it all over. Probably my favorite example of its use, though, was in the Xbox 360. So if you're not aware, IBM did the hardware for the Xbox 360. Part of doing a hardware architecture is you have to design a memory interface protocol, and that's how your CPUs talk to your RAM. IBM's brilliant engineers put together a protocol in the sort of semi-formal way that a lot of people in the hardware industry usually do, and they passed it off to Microsoft. A manager at Microsoft took this in, and he said, hey, you summer intern, come over here. He grabbed his summer intern and said, you need something to do. I want you to convert IBM's semi-formal spec into TLA Plus. In doing this, this summer intern found a bug that would have caused every single Xbox 360 to hard lock after 4 hours of consecutive use. Fortunately, they found it before they started actually building the CPUs. All right. So there is a little bit of real-world use. Yes, TLA Plus can actually work on systems that anyone here works on. All right. Now, I want to give you a few quotes because they'll nail down a couple points that I find are important. These are all from Chris Newcomb. He's a former AWS principal engineer. He was at AWS, I think, for almost a decade. He was at Valve before that. He helped build Steam. He's a super smart guy. He said, at Amazon, many engineers at all levels of experience have been able to learn TLA Plus from scratch and get useful results in 2 to 3 weeks, in some cases just in their personal time on weekends and evenings and without help or training. The reason I think this is so important is because I don't want you walking out of here thinking, oh, I've got to go do a grad school course or 2 years of training to have any hope of using this. Anybody who is a software developer and understands software development can do this, can learn it on their own. There's great resources out there. He also said executive management are now proactively encouraging teams to write TLA Plus specs for new features and other significant design changes. In annual planning, managers are now allocating engineering time to use TLA Plus. It's so successful that managers are willing to tell engineers to do something other than write code. That's pretty rare. And finally, again, remember how accomplished Chris Newcomb is and all the things he's built? He says, TLA Plus is the most valuable thing that I've learned in my professional career. It has changed how I work by giving me an immensely powerful tool to find subtle flaws in system designs. It has changed how I think. All right. I think that's pretty important. So the last thing I want to leave you with is the Raft algorithm. You may have heard of it, you may not have. It is a used heavily in industry consensus algorithm that was designed with TLA Plus. Okay, the biggest package you might have heard of that uses Raft as its basis is etcd. And this is used by Kubernetes. I've heard Kubernetes might be used in a few places now. Thus, the Raft algorithm is very important to the correct execution of Kubernetes. And what's etcd? It's a distributed key value store where every server must agree on the key values. So you could have 3 or 5 servers around the world that are all keeping basically copies of the key values, and you have to make sure that they all agree on what the values are. If there's a disagreement, you have a very fundamental problem. And the correctness of this was shown in the Raft algorithm using TLA Plus. So I want to pull out a little tiny bit of the spec. This is lines like 41 to 493. The whole spec for Raft is about 500 lines long, and that's a good point as well, because even the biggest systems, the TLA Plus spec is rarely over 1,000 lines long, because you're working at a high level of abstraction. You don't need all the boilerplate, all the code that goes with actual implementation. So the Raft spec, very important spec, used heavily around the world. It's about 500 lines long. The reason I like to point it out is for a few lines here. The person who created the Raft spec understands that in a real system, VMs randomly restart, right? Bad things happen. We have faulty networks and faulty hardware all the time. Things happen. So into the spec, he has explicitly modeled the possibility that at any time, any server can restart. At any time, any server can time out. The servers can do useful things too, and network messages can be successfully received, but at any time, any message might get duplicated, or any message might just randomly get dropped. This happens in real systems. And even in the face of all of this, the spec is correct. And TLA Plus makes this sort of thing possible because you can explicitly model errors in your system and make sure that your core algorithm and the core system you're writing is able to survive in the face of those errors. So that's it with the Raft spec. I want to make sure this gets up there so in the video people can get these links. For something that's used as infrequently as TLA Plus is, or not infrequently, but it has such a small community relative to a lot of other things, there are a ton of fantastic resources out there. These are just some of them. These are my favorite ones. So I'll leave you with that. It looks like I'm out of time, and I don't want to hold anybody up for lunch. So thank you very much.